Hey, so this is problem number 2 of homework number 6. X and Y are IID random variables. IID stands for identical and identically distributed random variables with a common PDF probability density function. Um, f of x equals to e to the negative x with step function of u of x, and f of y is equal to e to negative y with a step function of u of y. And we're supposed to find the probability density functions, which is the little f of x or little f of y, of the following variables: random variable x plus random variable y, random variable x minus random variable y, random variable x times random variable y, and random variable x divided by random variable y. Okay. And we are also given these two graphs of f of x and f of y. So the first part, I'm going to use convolution to figure out the probability density function of x plus y. Pretty much, so z, x plus y equals to z, which also equals to x equaling to negative y plus z. Another way to say that is y equaling to negative x plus z. So by using the convolution method, as stated in last week's homework, you take the you take the integral from negative infinity to infinity of f of x times the f of y z minus x dx. This was a large part of the first problem in the last week's homework. And basically you just it's like spelled out for you right there. You use z minus x, and you just take do the integral of that whole thing, and you end up with a probability density function of z times e to the negative z. And normally, my first instinct was to find the probability mass function and then find the probability density function by taking the derivative of the probability mass function. But this way could be done as well. In B, there are two parts. So this is where you see me finding the probability mass function first and then taking the derivative of that. You have you have the random variable z equaling to the random variable x minus random variable y, or random variable x equaling to random variable z plus random variable y, or y equaling to random variable z plus random variable x. So basically the probability mass function of z, you take the double integral of f of x, f of y, which we proved last week, from 0 to infinity, for, I think I may have missed something. Let me check in my scratch work. Yes, I did miss something. So, okay, so there should also be a dx in here. Sorry. Okay. Oh no, this is already done. Should be a dx in there. So, all right. So basically, you just evaluate this integral to find the probability mass function. I'm not going to go through the integral because my phone is running out of memory. But the learning part here is that we know how to find the probability density function from the probability mass function, but what are the bounds? How do you know what the bounds are? And basically, I don't have the graph here, but when I graphed z equal to negative x minus y, there were two lines, and from both lines, this was the first line. I found that the bounds x, as you can see, the inner integral is dx, x equals to y plus z, and that's how you find the bounds. If you want to do without the graph, which I normally do, but is not suggested, so that's how you kind of find it. And so after working out the entire integral, you get e to negative z over 2 plus 1. You take the derivative of that, and you end up with a probability mass function or density function of e to the negative z over 2, but that's only for z greater than 0, as I've told you when I graphed it out. And so this is the second part right here. Same thing, you do the integral, but the bounds are different this time because here in the first part, you can see it's from 0 to infinity. But here, in the second part, it's from negative z to infinity. Same thing for the inner bounds of dx. The inner bounds of dx from 0 to y plus z. And then you just work out this integral, and eventually you arrive at e to the z over 2 for z is less than 0, when the graph is of z is less than 0. Okay, so B was the hardest part. C is very simple. Same thing. We're doing so. The way to do these problems was to find the probability mass function. Like I said, take the derivative of that to find the probability density functions. So here z, random variable z, equals to the random variable x times random variable y, or random variable y is less than or equal to z over x, or x random variable x is less than or equal to random variable z over random variable y. Okay, so you're bound. So I chose to use dy inside first, and then so from 0, this would be from 0 to x, right? But x is less than or equal to z over y. So that's why the bounds over there are, excuse me, y. I'm doing the inner integral is y. So the inner bounds is from 0 to z over x because y is less than or equal to z over x. Okay, so you work out the integral, and eventually you arrive at Professor Chen asked us to leave it in the integral form, so that's what I did. But when you leave it in the integral form, which is the integral from 0 to infinity of negative e to negative x minus z over x dx plus 1, when you take the integral, not the integral, the derivative of this, the 1 disappears. So basically you're just left with this integral, this incomplete integral. And the u of z signifies that everything is positive. The u of z is the step function, and step functions make all functions positive. And so this is for the from z to greater than or equal to 0. Okay, and then finally part B, all spelled out here for you, or mostly spelled out here for you. So x over y is equal to z, or x is equal to zy, or y is equal to x over z. I believe, yes. Y is equal to x over z. So what I did was I used dx as the inner integral. So x equals to zy, right? So since we're using it in terms of x equals to zy, so that's why your bounds are zy. So yeah, that's how I usually figure out my bounds. And then the outer bounds is from 0 to infinity for dy. So you evaluate the integral, and you end up with 1 minus 1 over 1 plus z as your probability mass function of z. You take the derivative of that over here, and you get 1 over the quantity of 1 plus z squared for z is greater than or equal to 0, or if you want to do the step function, add the step function, which shows that everything is greater than or equal to 0, then you add the step function of uz. And this pretty much, these are analogous. And that's it. Thank you.